This is part 2 of our discussion of ionic and covalent bonding general concepts. You'll recall in the last recording we left off showing how bond energies could be used to calculate the delta H, the enthalpy change for any chemical reaction for which we have the bond dissociation energies of the various connections between the atoms. There are larger tables than this, but this is a fairly comprehensive table of bond dissociation energies that can be used for that purpose. And you can find these on the internet and, of course, in the Handbook of Chemistry and Physics. The next thing we're going to talk about is electronegativity. This is Dr. Pauling's invention, and as you can see, we have fluorine as the highest electronegativity. It is the smallest of the atoms and has the greatest attraction of its outer electrons, its valence electrons for the nucleus. And we come down here to cesium, which is an element that he knew when he put this table together, and it's down at 0.8. So electronegativity is the ability of an atom and a molecule to attract shared electrons to its nucleus, towards its nucleus. And it can be used for a number of things. Now, one thing it can do is it can tell us whether a bond is polar covalent or nonpolar covalent. And that has to do with the difference in electronegativities. When electrons are unequally shared, we have a polar covalent bond, a bond in which the electrons spend more time towards one atom than the other, towards one nucleus than the other nucleus. This can be seen when you have electronegativity differences that are higher than 0.3 and lower than 1.7, because 1.7 is really our trigger for saying that a bond is not covalent, but rather is ionic. Nonpolar covalent bonds, we have electrons being equally shared between the two atoms. They are attracted pretty much equally towards each nuclei. The electronegativity difference there can be 0, for instance, if you have hydrogen-hydrogen, or chlorine-chlorine, or 0.3, which is typically what we think of between carbon and hydrogen. Let's go ahead and recap what we know about ionic bonding before we get into a new topic. In ionic bonding, electrons are transferred from one atom to the other. Forming then from the metal, you form a cation, in this case the sodium plus ion, and on the other hand the anion, which is in this case a chloride ion. The sodium ion has a plus charge because it's lost one of its electrons, its valence electron. The chloride is negatively charged because it's picked up that or some other electron that has been given away. As I mentioned earlier, electronegativity differences in ionic bonding are generally considered to be greater than 1.7. The formation of ionic bonds, remember, is always exothermic, because the energy of the two atoms, the sodium in this case and the chlorine in this case, is always higher than of the two ions after the chemical reaction. Bond polarity can be pictured using partial charges. Now, these are not true charges, but they tell us in what direction the bond is tending. So, for instance, in hydrogen chloride, which is a molecule, this is the gas, not the hydrochloric acid in water, the hydrogen is less electronegative than the chlorine, and therefore the hydrogen has less time with its electrons, the electrons of this single bond, the two electrons, has less time than the chlorine does. And so this is a polar covalent bond. In this case, the plus, the partial plus and the partial minus is shown here, and the difference between them is 0.9. If you have an electronegativity difference between atoms of 0 to 0.5, we consider the bond type to be nonpolar. If it's 0.5 to 2, we consider it to be polar, and we really said 1.7 is the trigger point. Above 1.7, we would consider it to be mostly ionic. This is a picture, just a representation of the electron distribution, the electron cloud, if you wish, the mosquito graph of the hydrogen chloride molecule. And this is, of course, a polar covalent bond. The highest electron density is around the chlorine nucleus, and the lowest density is in the vicinity of the hydrogen. The bonding electrons, this electron pair, are attracted more strongly by the chlorine than by the hydrogen. Now, let's look a little bit at resonance. Resonance occurs when you have multiple polar bonds, or they don't have to be polar, but they usually are. Multiple bonds, covalent bonds, and you're looking at usually 3, occasionally 2 atoms. It could be more, it could be a larger number. For instance, in benzene, you have 6 carbons in a ring shape. But let's look at a simple system with N2O, dinitrogen monoxide, otherwise known as laughing gas, and it has 3 resonance forms. You can draw the Lewis structures 3 different ways. You can see them here. You can count up the electrons on the nitrogen. 5 valence electrons each makes 10, and then the oxygen raises the total by its 6 to 16. So you'll count 16 electrons on each of these. You can draw them 3 different ways. Which is the right one? Really, none of them are the only way the electrons are found. In fact, there's probably a sharing of the types. The electrons, as you know, are in clouds, and they can wander about over the molecule. So how do we figure out which one contributes most to the overall electronic structure? That's going to have an impact on the way it reacts and on what can attack and at what end a substituent can attack this molecule. So let's look at a way to determine which one contributes most to the overall electronic structure. And it's called the assignment of formal charges. What we're doing, we have covalent bonding in a molecule, and we know they're sharing, but we assume, we treat it, we have an accounting technique that assumes that the bonding electrons are not shared equally, that we know they're not shared equally, but we assume that they are. In other words, we give them a formal charge, and that will help us to determine which is the more likely of these resonance structures to be correct. And for any atom, the formal charge is the number of valence electrons on that atom. So right from the periodic table, you're going to subtract the electrons that are not bonded at all on that atom, and you're going to subtract half of the electrons that are bonded on that atom. So it's a simple accounting method. It does not tell us the exact chemistry, but it will help us to determine the primary resonance structure. So let's look at our friend here, N2O, and look at this structure. And let's talk it through. Nitrogen has 5 valence electrons, so we start off with a 5. And how many non-bonding electrons do you see? Oh, 1, 2, 3, 4, 5, 6. So we're going to subtract 6, and 5 minus 6 is minus 1. Then we subtract half of the bonding electrons, and you see that between the 2 nitrogen atoms. There's 1 bond there. So we subtract 1 from a negative 1, and we get negative 2. So you see the formal charge on this nitrogen is negative 2. Good. This nitrogen next door to it, the one right in the middle, 5 valence electrons like all nitrogen. we subtract the non-bonding electrons. Well, there aren't any. They're all bonded. There are, in fact, 4 bonds, 3 to the oxygen and 1 to the other nitrogen. So that's 8 electrons. We subtract 4 from 5, and we get plus 1. Finally, we go to the oxygen, and oxygen has 6 valence electrons. We subtract the non-bonding. There's 2 on the right end. There's a non-bonded pair, the lone pair on the right. So we subtract from 6, we subtract 2, and we get 4. So that's a plus 4. And now we have 1, 2, 3 bonds to the nitrogen. That's 6 electrons. We subtract half of those, that's 3. So we're down to plus 1 for this oxygen. Now, what's wrong with that? Well, nothing's wrong with that, but we know that oxygen is far more electronegative than nitrogen is. So it's more likely to have the electrons in its area than the nitrogen is. So maybe that's not quite the best structure. Let's look at another one. Here we have the double bonds between the nitrogens and a double bond between a nitrogen and oxygen. This is a little better because, and I suggest you do this, go ahead and do the math. The nitrogen on the left is a -1, the one in the middle is a +1, and the oxygen is now at 0. Now, that's still not what we would like to see because oxygen still has more attraction for electrons than nitrogen does. But it's certainly better than the resonance structure on the left. The final one that we showed you is this one. Here, and let's just do the oxygen. The oxygen has 6 bonding electrons. It has 6 electrons that are not bonded, 3 lone pairs. So we subtract 6 from 6 and we get a 0. And it has the 1 bond to the nitrogen. We take off half of that pair and we are ending up with a -1 on the oxygen. This is the preferred structure, it would have to be, because the oxygen is the most electronegative. The most favored resonance form is the one that has the smallest formal charges, no formal charges with the same sign on adjacent atoms, and on the most electronegative atom, you want a negative charge. So, the most favorable, as we mentioned before, is the one on the right because the oxygen has a negative charge and it is the most electronegative of those 3 atoms. So your turn. Go ahead and stop the video and assign formal charges to the 3 resonance structures of the cyanide ion, and remembering that nitrogen is the more electronegative of the 2, see if you can determine which of these 3 structures is the most likely to be true among the Lewis structures. Remember too also that this has a negative charge, and so there's 1 more electron than you would expect to find on a CN combination like this.